So we're looking at vertical forces here. And if we recall, whenever we're talking about forces, what we're really talking about is this idea of F equals ma, where the sum of all the forces, so however many forces you have to add them together, equals an object's mass multiplied by its acceleration, okay? Now, one of the interesting things about forces is that forces going to the left and right in the x direction, they're independent from forces going in the vertical direction, up and down. We can basically break them up into x components and y components and treat them as such so that we can add them up independently. To do this and to kind of start thinking about this, it's important to recognize that most objects have a weight pulling on them. You know, if you jump out of an airplane, what is actually causing you to fall? You know, if here's an airplane poorly drawn by yours truly, this is how I've always drawn airplanes, so they smile. But if you've got an airplane and you jump out of the airplane, what's going to happen? Well, here's you. That's a free body diagram image of you. You're going to fall down. Well, what's causing you to fall down and accelerate downward? Well, that is your weight. And in the world of physics, your weight is equal to your mass multiplied by gravity. And if we actually look at this equation here, weight equals mg, weight is an amount of force, okay? It's a push or a pull. Specifically, it's a pull. The Earth is pulling you down to it. It's pulling you inward towards the center. So this weight here is really a force. And mass is a mass, and we know that gravity, well, gravity is an acceleration. So this equation, F equals ma, is the equation W equals mg. And that's what we see right here. These equations are the same. It's just saying, look, a specific force, which we can call the weight, is just mass times the gravity on whatever planet you're at. Okay, and on Earth, we know that to be 9.8. Earlier in the year when we were doing projectiles, we often said that gravity was like negative 9.8 meters per second squared. But remember, that negative is just because we called down the negative direction. So if you called down negative and up positive, then sure, that would be a negative 9.8. But when we talk about forces, it's often easier to think about, hey, we made the force negative. Let's just pretend the 9.8 is a positive number and the force itself is the negative quantity of it. And we'll see how that looks moving further on. And this is just so that if we wanted to make down positive, we could, and everything would work out. So when we think about weight, that is what is physically pulling us down towards the center of the Earth, towards the ground, what we have going on there. But whenever you step on a scale, the scale isn't actually measuring your weight, which is a little weird thinking about that. You can trick a scale pretty easily. You know, if here's a scale on the ground and you're standing on it, it should read your weight, right? But what if you were also kind of holding your body up on like a towel rack in your bathroom? Then all of a sudden you'd weigh less, right? Well, you wouldn't weigh less. You still have the same amount of weight. Remember, your weight is just your mass multiplied by gravity. You haven't changed your mass. You haven't, like, I don't know, chopped off your arm or something like that. You're still you. So why does your scale say you weigh less all of a sudden? Well, it has to do with the fact that your scale isn't measuring your weight. Your scale is measuring your apparent weight. Your scale is measuring the push back from the ground up on you. Remember those action-reaction forces? You push on the ground pushes back up on you. That's what your scale is actually measuring. Your scale is measuring your normal force. So if here's you standing on the scale, there's your weight acting down, but your normal force is acting up. It just so happens to be that when you stand normally on a scale, your weight and normal force are the exact same, and that's why you don't sink into the ground, and you also don't start floating away into the sky, because they're equal. So you're going to maintain your velocity, and if you're just standing there, that velocity is zero, so nothing happens. But what happens if we are in some sort of object that is accelerating up? What if you're in something like an elevator? So what if you're in an elevator here, and the elevator starts to accelerate upwards? Well, you may have experienced this sensation before. If you've ever been in an elevator, which odds are you probably have, what I like to do, and this freaks people out, there's a ton of things in an elevator you can do to freak people out, but one of the things that I like to do is to walk in a circle on the elevator, especially if I'm by myself in the elevator. Even weirder whenever people are there. But if you walk in a circle or even just march in place in an elevator, when that elevator begins to move and lift you upwards, all of a sudden you get, you feel a little bit heavier, right? You feel like, whoa, why do I feel heavy? But it's only for like a quick little moment. You feel heavy for a moment. And if we think about that, why would we feel heavy? Well, if here we are in an elevator, we have our weight pulling down on us. And that weight isn't changing. Like I said, you haven't chopped off your arms yet. But all of a sudden, you're accelerating upwards. So there needs to be another force acting on your body. This means that when the elevator pushes up on you, your normal force is actually larger. So your normal force here is larger than the weight, okay? This would also apply if you were doing something like, imagine you were fishing and you had some sort of like fishing line and you're pulling something out of the water with it. As you accelerate it upwards, that fishing line gets more tension in it. Okay, so the normal force is going to be greater than the weight, or if you had some sort of like cable system that you were doing this with, you could say that the tension would be greater than the weight if you were doing this with, you know, a rope or a chain or something like that. So as you pull things and accelerate them upwards, and the key is to accelerate them upwards. We're not just pulling them upwards, we're accelerating them upwards. We're moving them faster upwards. We see that this normal force or the tension would increase and it would be greater than whatever the weight is. And the reason why it's so important to accelerate upwards, to move faster, is because if you're at a constant speed, your acceleration is 0. If we go back into the elevator, when it first starts, you feel like you're getting heavy for a moment. But then everything feels normal again. It doesn't feel like anything. You just kind of hear the elevator go, and then all of a sudden you're magically on the 80th floor. Like, ta-da! Well, what's happening there is, here you are, your weight is pulling you down, because that's your weight, and the normal force is equal to your weight here. And since they're equal, you won't have a net acceleration. Your acceleration will be 0. And this means that you just feel the exact same. The human body is set up not to feel velocity, to feel speed. It's set up to feel accelerations. That's why you've probably experienced this one too. Sometimes you like lay in your bed at night, and then all of a sudden you feel like you're falling, and then it's like, what the heck was that? Usually out of nowhere. Your body feels accelerations, but you could sleep in a train or you could sleep on a plane. Your body doesn't feel velocities, it feels this acceleration. So when you're at a constant speed, your normal force, the force pushing back up on you from the ground, is equal to the weight. And if you did this for a rope, your tension would equal the weight too. And that's why it's so important that if you are pulling a large fish out of the water, you pull them at like a nice constant speed, because if you pull them quickly, you're gonna snap the line. So a nice steady speed, the acceleration will be 0, and the tension will just equal whatever the weight is. Now our last kind of scenario here is if we are falling down, like London Bridge. Well, in this case, our acceleration is in the downward direction. And if we go back onto that elevator, this is like you're on the 80th floor, and then you go down to the lobby, right? So your acceleration is downward now. Well, if you do the little march in place thing in that case, it feels like for an instant you begin to fall. And if you, I know it's not a ride anymore, but it used to be a ride at Kennywood. The pitfall, where you just go to the top and they just drop you down, or pretty much any ride at Kennywood where you're brought up to a large height and then drop, like the Sky Coaster. Anytime you're falling like that, you feel that initial acceleration. You feel your stomach like go up into your gut and throat and And what's actually happening there is you still have the weight. All of these weights are the same. You're still you. But because nothing's pushing back on you, or in the elevator situation, it's pushing back on you less, boop, a very tiny normal force. What will happen in this case is the normal force will be less than the weight. And because of that, you have a net force pulling you down, and you're going to fall. Likewise, if you're holding something with a chain or a cable and you are accelerating it downwards, the tension will be less than the weight as well. Okay? And that makes a ton of sense. If you go really quickly, you're holding something with a cable and you just go down fast, that cable can sometimes, if you move fast enough, it'll lose its tension in it. It'll just come slack for a second until the mass, the bottom piece, actually begins to fall again. So if you've ever seen something like that, it's the same idea going on there. Okay, so depending on if you're going up at an accelerating rate, okay, you're accelerating upwards, your normal will be greater than the weight. If you're at a constant speed, then tension and normals will equal the weight. And if you're accelerating down, you're falling, the tensions and normals will be less than your weight. So with this idea of normal forces and tensions and comparing them to weights and this idea of vertical motion, let's look at a F equals ma problem, Newton's second law, in a vertical case. So one of the vertical cases I like to think about is, if you've ever gone down to the Strip District, there's a fish store down there called Woolies, and you can buy all sorts of fish, and fish is often sold by the pound, right? Or in our case, by the mass in the kilogram. And I've always thought it would be interesting if you walked into an elevator and there was just like a fishmonger there selling their fish, on ice, but in an elevator. And if you ever see someone selling fish in an elevator, you should be a little skeptical of them, because depending on when you buy that fish, you may be overpaying, or if you're the clever physicist and you outsmart them, you could be getting that fish on a discount. And this will apply to anything you buy by the pound. So deli meats or fancy cheeses, whatever. This will apply there. So in our scenario here, we've got a 5 kilogram salmon, and it's weighed from a fish scale attached to the ceiling of an elevator. So if you've ever been, seen a fish scale, you just hang a fish from it. But this is a similar idea to, if you put apples or produce on one of those produce scales in like a giant eagle. It says how much they weigh or what their weight is, okay? So what we would like to know is just what is the apparent weight of the salmon in the elevator for these three scenarios. At rest, when the elevator is accelerating upward, and when the acceleration is downward in the elevator. So the first thing we're going to do, and it's always nice to do this, let's just draw it to the side, is create a free body diagram of this scenario. So take a second here and draw yourself a little free body diagram of this scenario. Then I'll draw mine, and we can check them, and we can see how this goes. So our free body diagram, when we draw it, will be the fish, which is just a dot. It will be the weight acting down, W equals mg, and it's always nice to label these. And then the actual thing holding the fish up is the tension, okay? And that tension is our apparent weight. So if we want to try to figure out what is that tension, what is that apparent weight when the elevator is at rest, well, when the elevator is at rest, what's the acceleration? That acceleration is 0. So if we set up a F equals ma equation, the sum of the forces equals a mass times the acceleration, we can solve this. We should know the answer is just the tension will equal the weight, because our acceleration is 0. But how can we prove that? Well, let's pick a direction first. We can either pick up or down to be positive. It doesn't matter what you pick, but you need to make a decision. Most people feel comfortable picking up as positive, because that's kind of the math thing to do. So let's just do that. But if you want down to be positive, nothing wrong there. So up is positive, down is negative. And if we write out our forces equals ma, well, let's add these together. A positive tension plus a negative weight, so that's like minus the weight, equals ma. And since our acceleration is 0, the mass, which is 5, times 0 is 0. And if we wanted to solve for tension, well, we could just move weight to the other side. We see that the tension is equal to the weight, which is equal to mg, because we have that in this equation right here in green. And that means if we just take the 5 kilograms times the 9.8 meters per second squared for gravity, we get the tension here for part A is just 49 newtons. Okay, so that's our answer for part A there. So for part B here, I want you to try this now. you have the same scenario. You're weighing the salmon, but the elevator has started to move. You're now accelerating upward at a rate of 2.5 meters per second squared. So try to set up this F equals ma equation. Pause this video, try that out, and then when we unpause, when we continue, we'll see how we do this, okay? Okay, so let's see how we go ahead and solve this then. So we're accelerating upwards at 2.5 meters per second squared. So let's just go to our diagram and just say that our acceleration is upwards here. So it has to be positive. So if we go and set up our F equals ma equation again, nothing's going to change in it. We still have a tension minus weight. A positive tension minus a weight equals ma. So we're going to have a tension, which is what we're looking for, minus a weight equals ma. And if we put in some values here, we'll see we have tension minus, well, we know the weight is 49 mg. 5 times 9.8 was 49. And that's going to equal the mass, 5 kilograms, multiplied by the acceleration. And our acceleration is a positive 2.5. So now we can take the 5 and 2.5, multiply them together, and then we can combine them with the 49. So if we go ahead and solve this, 5 times 2.5 is 12.5. So we get t minus 49 equals 12.5. And then if we add the 49 to each side, we get that the tension is equal to, oh, we get there. 12 and 49 is 61.5 for the tension. So it appears, and it's true, that if this elevator is accelerating upwards, all of a sudden the salmon looks like it weighs more. It's still the same salmon, but it looks like it weighs more because the apparent weight is larger. So if you bought this salmon when the elevator is accelerating upward, you're going to overpay. You're going to overpay by like 10 to 12% on the salmon. Now, if you're the clever physicist, you can kind of get around this. Okay, so let's just solve the last part here. We're now going to accelerate downwards at 3.2 meters per second. Since our acceleration is downwards now, it's going to be negative. So same equation, t minus 49 equals 5 times negative 3.2 meters per second squared. I know all the units are going to be newtons here, so that's good. 5 times negative 3.2 gives me negative 16. So t minus 49, 9, not a 6, equals negative 16. We then simply add the 49 to each side, and we find that the tension in this case is only 33 newtons. So if you were accelerating downward in the elevator, you'd actually pay less for the salmon because the weight would look like it was less here. The apparent weight that the fish scale is reading is only 33, when in reality, it should be 49. And if, the sucker accidentally paid when you're accelerating upward and paid 61, oh boy, they paid nearly double of what you did when you're accelerating downward. So this is the idea of an apparent weight. It's an idea of vertical forces. It's still just F equals ma, but we're including weight into these problems and recognizing that the tension, or the normal force, if we want to think about it that way, can change depending on if we're accelerating up or down. Okay? And that's where we'll be.